video lecture. I am Dr. A.VELMURUGAN, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Chettikari, Dharmaburi. In this video lecture, from upcoming semester Thermal Engineering 2, Unit 3 Steam Turbine. Previously, we have to discuss about the Module 1, introductions of the steam turbine. From Module 2, the pressure compounding, velocity compounding, and pressure velocity compounding. From Module 3, we have discussed about the impulse turbine. From that simple impulse turbine, it is a primarily consists of a nozzle or a set of nozzle, a rotor mounted on a shaft, one set of the moving blade attached to the rotor, and a casing. A simple impulse turbine is also called D-level turbine after the name of its inventor. This turbine is called simple impulse turbine since the working expansion of the steam takes place in one set of the nozzle. So previously I have discussed about the D-level turbine. From this section there is a longitudinal section. From here, from the upper portion there is a nozzle and a blade profile. From this D-level turbine, that is a single stage turbine. From the shaft is moving on the axial direction, but the blade is rotating on the circumferential direction. The high velocity steam is entered to the nozzle. From that nozzle section there is a pressure drop in the nozzle section, but in the blade section there is no pressure drop. There is no any changes in the pressure level, but in the nozzle there is a nozzle velocity will be increasing from the nozzle section. From that blade section the velocity will be decreased. Already I told about you that the last from the velocity is 10 to 12% of the kinetic energy. From these basics of the impulse turbine, in impulse turbine the steam coming out through a fixed nozzle at a very high velocity to strike the blade or glides the blade fixed on the periphery rotor. The blade changes the direction of the steam flow without changing its pressure. The force due to the change of the momentum causes the rotation of the turbine shaft. Example: D-level turbine, Cortis turbine, velocity compounding, Rative turbine for pressure compounding. From this impulse turbine consists of basically of a rotor mounted on a shaft that is free to rotate in a set of bearings. The outer rim of the rotor carries a set of covered blades and the whole assembly is enclosed in a airtight case. Nozzle directs steam against the blade and turn the rotor. The energy to rotor on impulse turbine is derived from the kinetic energy of the steam flowing through the nozzle. The term impulse means that the force that turns the turbine comes from the output impact of the steam on the blades. From that impulse turbine, the toy pinwheel can be used to study some of the basic principles of turbine. When we blow on the rim of the wheel, it spins rapidly. The harder we blow, the faster it turns. The steam turbine is operated on the same principle, except it uses the kinetic energy of the steam as it leaves a nozzle rather than air. The steam nozzles are located at the turbine inlet. As the steam passes through a steam nozzle, potential energy is converted into kinetic energy. The kinetic energy is converted into mechanical energy to useful shaft work from the turbine rotation. The steam is directed towards the turbine blades and turn the rotor. The velocity of the steam is reduced in passing over the blades. Some of its kinetic energy has been transferred to the blades to turn the rotor. From that, impulse turbine may be used to drive the forced draft blowers, pump and main propulsion of the turbines. From the construction and working principles of the impulse turbine, from the uppermost section of the diagram is the longitudinal section through the upper half of the turbine. The middle portion of the section of the turbine is that is the shape of the nozzle and blade section. From the bottom portion of this section is the variation of absolute velocity and absolute pressure during the flow of steam through passage of the nozzle and blades. From the expansion is happen on the turbine stage, the initial pressure, that is a steam chest pressure, and the final pressure is a condenser pressure, takes place in one set of the nozzle. Due to the high drop pressure in the nozzle, the velocity of the steam in the nozzle is increases. From the steam is leaves the nozzle is very high velocity and strikes the blade to rotate the turbine mounted on the wheel with its high velocity. The loss of the energies due to higher exit velocity is commonly known as carry over loss or leaving losses. From that high velocity steam is entered to the turbine. From that leaving losses, that is a 10 to 12 percentage loss of the kinetic energy. That loss is known as a carryover loss or leaving loss. From the pressure of the steam, when it moves over the blades remain constant, but the velocity will be decreases. The exit, leaving and lost velocity almost 3.3% on the nozzle of the outlet velocity. Also, since the kinetic energy is to be absorbed by one ring, of it will be the blade will be rotating from the RPM is very high to 25,000 rpm to 30,000 rpm. However, the wheel or rotor speed can be reduced by adopting the method of two compounding of the turbines. The disadvantage of this impulse turbine is since all the kinetic energy, the high velocity steam has to be absorbed only one ring of moving blades. The velocity of the turbine is very high up to the blade will be rotating for 30,000 rpm from the practical purpose. The velocity of the steam at the exit is sufficiently high, which means that there is a considerable loss of kinetic energy. From this figure, we have to very important from the problem point of view, very you should understand about the velocity diagram and velocity triangle of this impulse turbine. From this upper section is inlet velocity triangle, from the lower section is outlet velocity triangle. Generally, the nozzle from the high velocity steam is hit the or impinges or sliding the blade from that blade velocity. That is, the blade will there will be some exerted force will be acting. If that from that axis motion in the shaft and the circumferential motion in the blade, we have to rotate the blade. From that high velocity steam is impinges or glides the blade to rotate. There will be some reaction is formed. So that's why we should find out the inlet velocity triangle from the velocity of the single diagram, that is a velocity diagram. From the steam jet issuing from the nozzle at a high velocity V1 at an angle of alpha 1, from at an angle of alpha 1, the tangential component from the jet, that is a VW1, the perform work on the blade, that the axial component is, that is a axial velocity is VA1. As the blade moves at the tangential velocity of VW1, the entering the steam jet has a relative velocity. From the relative velocity is VR1. With respect to the blade angle is beta 1. From the inlet angle is alpha 1, the blade angle is beta 1. Simultaneously, the steam that then glides over the blade without any shock and discharge at a relative velocity of V2 at an angle of alpha 2 with a tangent of the blades. From that, the steam will be leaving from the outlet of the velocity triangle. The absolute velocity is V2 at an angle of alpha 2. From this blade angle, from that relative velocity, that is a beta 2, the relative velocity at inlet VR1 is same to the relative velocity of outlet velocity triangle. If there is no frictional losses at the blade, the absolute velocity of the V2 of the leaving steam make at an angle of beta 2, that is the tangent on the wheel. From this combination of the velocity from the single diagram, that is a velocity diagram, the velocity U is the common for all. From this combination of velocity triangle, the velocity from the single diagram, that is a velocity diagram. From that section A to B, that is the velocity is common to all the cases. The velocity of the blade, from the velocity of the blade at an angle of alpha 1, at an angle of alpha 1, that is from the angle of alpha 1, there is a relative velocity. From the blade inlet angle is beta 1. Regarding to the VR2, that is this is a inlet velocity triangle. From that inlet velocity triangle, the velocity is V1 at an angle of alpha 1, and from that blade angle there is a beta 1, the relative velocity is VR1. This section is this is called inlet velocity triangle. We have to find out the output of the velocity triangle. It is very easier to find out the combination of this combinedly. We have to mix with the inlet velocity triangle and outlet velocity triangle. Regarding to the relative velocity of VR2 at an angle of beta 2, outlet angle. Combined we get velocity V2. This angle is a alpha 2. Certain component of this velocity is producing to output. From this slide we have discussed about the work output, power blade efficiency and stage efficiency. First of all, you should find out the force in the tangential direction, the rate of change of momentum in the tangential direction. It is mass per second into change in velocity in newtons. From the change in velocity from the newtons is mass per second m dot into VW1 plus VW2 in newtons. That is a VW1 and plus VW2 is a uh, section of section of the whirl component from the section of A to E from the inlet section VW1 from the outlet velocity triangle, that is a VW2. From the force in the axial direction, from the ideal condition there is no any axial thrust. Generally we have to axial motion, we have to rotate the shaft, but in the blade is rotating from the circumferential motion. There is no any friction is happen on the axial thrust. From that axial thrust we have to rotate the blade with the help of this high velocity steam, that is a rate of change of momentum in the axial direction. From that combined velocity triangle, this is the axial thrust is happening from that inlet triangle and outlet triangle, that is axial thrust is VA2. From that axial direction, the rate of change of momentum in the axial direction. Finally, we find out the work done by the steam of the blade, that is mass per second into the final output, that is a VW1 plus or minus VW2 into the blade velocity Newton per second. The very important for that power output from the output of the turbine, there is the three things. One thing is power output, second thing is blade efficiency, third thing is stage efficiency. So very important from the problem point of view, you should find out the first thing is power developed, second thing is blade efficiency, third thing is stage efficiency. If you find out the blade efficiency, means the final work done from the output condition and also energy supplied from the inlet condition, that is a kinetic energy from that nozzle. From that work done is m into VW1 plus or minus VW2 into blade velocity divided by the kinetic energy 1 by 2 m V1 square. From here we have to remember this blade efficiency, that is a nozzle is acting on the nozzle efficiency. So 2u into VW1 plus or minus VW2 into u divided by V1 square. Finally we get energy lost due to the blade friction. From that energy lost from the blade friction from the inlet velocity triangle minus outlet velocity triangle, we get the final friction from the energy is 1 by 2 m VR1 square minus VR2 square Newton meter per square. Finally, we have to find out the third thing is stage efficiency. Work done of the blade divided by total energy supplied per the stage. Work done of the blade is m into VW1 plus or minus VW2 into u divided by the total energy supplied per the stage. That is a del H. That is a enthalpy drop from inlet triangle to outlet triangle from that outlet velocity triangle. M into H1 minus H2, that is a del H, that is H suffix D is equal to H1 minus H drop, that is a heat drop in the nozzle. From that maximum work and maximum diagram efficiency from the combined velocity triangle, we have that is from the inlet triangle, that is a VW1 whirl component V1 cos alpha 1. This can be right to, that is a V1 is equal to VR1, that is a VR1 is the relative velocity cos beta 1 plus u. From that outlet velocity triangle, the whirl component is VW2 is equal to V2 cos alpha 2 equal to VR2 cos beta 2 minus u. Because of outlet velocity, inlet velocity triangle minus outlet velocity triangle, we should find out the whirl component of the final output. VW1 plus VW2 equal to, we have to combine these two equation, VR1 cos beta 1 plus VR2 cos beta 2. Finally we get the, from the K is denoted for relative velocity of VR2 divided by VR1, from that C is denoted for cos beta 2 by cos beta 2. Finally we should find out the diagram efficiency, we get the reduce the equation and the final output of the diagram efficiency V1 cos alpha 1 minus u into 1 plus kc divided by v1 square. From here the rho is u by v1, that is a blade speed ratio. We get the diagram efficiency is equal to 2 into rho cos alpha 1 minus b square 1 plus kc1. From the problem point of view, you should mug up